So good afternoon, everyone. So I will commence the class now. I've commenced the recording so that I can share the recordings of the class after the class. So today, what I intend to do is to have some sort of revision with you with respect to special relativity. Thereafter, the questions I gave you as a assignment, we will then solve those problems together thereafter. But we need to go over what was taught because Brima requested, and I'm surprised now, he requested for the revision that he actually, some of you were complaining that you missed some of the classes. So that is the reason why I want to have something like a refresher so that we go over what special relativity entails, and thereafter we will then solve our problems. I'm trying to chat with Brima. So for today, we'll continue with the theory of relativity. And under this, we will, I hope you can view my slides. Can you view my slides?
Yes, sir. Yes, sir.
Okay. So now, relativity, it's actually a phenomenon which actually came into existence as a result of the movement of objects relative to one another, or yes, basically, at times two objects might be moving relative to each other, or at times one is stationary, the other is moving. So when you consider the law of physics, what happens to the law of physics as observed by both of them? So that was what brought about relativity. Under relativity, there are two forms of relativity. We have the special relativity. We also have the general relativity. We have the special relativity. We also have the general relativity. But we will be dealing with special relativity. General relativity basically deals with the discussion about terrestrial movements, such as the planet or the sun, the moon, moving relatively to each other. Now, one of the things we'll be discussing about is what is referred to as the inertial frame of reference. When you discuss about the inertial frame of reference, it is actually a frame of reference that is considered to have uniform velocity, or where uniform motion is taking place. That means no acceleration, you have uniform velocity, or uniform motion is in place within that frame. And when you talk about frame basically could refer to your coordinate. For the Cartesian coordinate, we have the X, we have the Y, we have the Z. So when you're talking about the frame, so if you have, for example, if you have an object within a frame of reference, let's say you have your Y, you have your Z, and you have your X. So if an object is within this frame of reference, it must definitely have some form of coordinate. So where it is currently, it's a frame of reference. But if that frame of reference is location is with a uniform motion, then we can discuss about the inertia frame of reference. We can discuss about the inertial frame of reference. So that's basically what we have when we discuss about this inertial frame of reference. So you can have two different objects. One might be in one frame of reference. Maybe it is inside a vehicle that is moving on the road, or inside the coach of a train moving in this direction, while you have an observer. You have an observer standing here watching somebody, whatever the person is doing within the train. So here it is stationary, your U is 0, but here it is moving with a specific velocity. So if you now want to compare, if they are discussing about an event, both of them, we want to see how they describe an event. For example, if just like I made mention of in the class, in the physical class, whereby I said if you are watching a football match, you see the referees, the referee and the linesmen moving up and down, but you find out that the spectators are stationary all day. So the way they will view the position of a ball for a referee to take a decision will be different from the referee that is moving up and down. The referee and the linesmen are in motion, while the spectators are stationary. So, and that was what brought about the technology FIFA actually introduced in terms of taking decision with respect to an event that takes place during a football match. Now, for example, if you have a light flash, maybe from a thunder, or lightning, you observe that this is common in Sierra Leone. You have lightning, and when the lightning strikes, and you have somebody on the surface of the earth, which is this man, is on the earth. The man on earth, he will see the speed at which the lightning travels. The lightning and the thunder, the speed at which it travels, the man on the earth will see it at this velocity. The man on earth will see it as that velocity. That is the velocity with which he will see the lightning move, which is in agreement with the proposition of Maxwell. Is in agreement with the proposition of Maxwell. Thereafter, if you now have a man inside a rocket, this is the rocket. If you have a man inside the rocket and you still have a man on the surface of the earth, the man in the rocket moves with the speed of v, while the lightning travels with the speed of c. So the man in the rocket will definitely see the speed of the lightning as c minus what? C minus v. C minus v, which is not in consonance with what Maxwell proposed. Because what Maxwell proposed is that each of them will view this the same way, the speed of the lightning. That is the proposition of Maxwell. Maxwell proposed that they will both see the speed of the lightning, they will see it being the same. But with this now, the man in the rocket will see the speed as being different. He's going to see it as being a different stuff. So what the speed of the lightning will look like to the man in the rocket is going to be the speed of the lightning minus the speed of the rocket. The speed of the lightning minus the speed of the rocket. So if you have questions, please, you can pause me and ask your questions. So do Maxwell's equation only work in one reference frame? And just like I made mention in the physical class, we have various Maxwell's equation. We have the Maxwell's equation, and Maxwell's equation are usually 4. So now the question is this: do they only work in one frame of reference, or they are the same in all frame of reference? If so, this will be the rest frame of the luminiferous ether. So if yes, that was what brought about the introduction of ether. That was what brought about the introduction of the ether. Because what Maxwell proposed was that it was going to be the same in all frame of reference. For example, now, the law of physics, what he proposed was that the law of physics is the same in all frames of reference. In all frames of reference. So that has been what was on ground. And that was what was proposed by Newton. It was what was proposed, that all Newtonian laws, Newtonian mechanics laws, are the same in all inertial frame of reference. But it got to a level where it's just like what we have here now. It's not the same. What the man on the earth will observe is not the same as what the man in the rocket is going to observe. They are not the same. So the speed of the lightning is not the same. So we now want to look at what is really causing this difference in the observation. What is causing the difference? And what brought about this difference? The law of physics. It got to a level where it could not explain the Maxwell's equation of electromagnetic radiation. The principle that was established could not explain that. So if so, the speed of light should change throughout the year. That is the implication if it's not the same. And we all know as a standard that the speed of light is 3 × 10⁻⁸. So if it's not going to be the same, that means the speed of light should change throughout the year. It should change throughout the year. So that is the implication. But when this was performed, the experiment of Michelson-Morley, it was observed that the existing law could not explain that. The existing law couldn't explain that. It couldn't explain that. So thereafter, we add this Einstein hypothesis. What was the proposition of Einstein? Number one, the two laws of Einstein, that the laws of nature are equally valid in every inertial reference frame. That the laws of nature are equally valid in every inertial reference frame. That was what he proposed. Now, secondly, he said the speed of light in empty space is the same for all inertial observer. The speed of light in empty space is the same in all inertial observer, regardless of their velocity or the velocity of the source of light. So now what Einstein did was these two laws. He said that the law of physics is the same in all inertial frame of reference. So after he said that, that means if you move from one frame of reference, maybe you move from physics department, FBC, you move to Strassakin building, Please, sorry for the spelling of this Sasakino, because I really do not know the spelling. If you move to Sasakin building now, maybe the dean's office, whatever experiment you perform here, if it's simple pendulum experiment, and somebody else at the dean's office is also performing it, you will have the same rule governing them. And that's why majorly what we have for simple pendulum, you always have that your T is equal to 2 pi square root of what? L divided by G. That's the standard stuff to calculate the period of simple pendulum. So the law of physics is the same in all inertial frame of reference. So the second one is now telling us that no matter the speed, it does not matter. Like now, you are in the physics department in the lab, you are stationary there, performing the experiment. If somebody inside a car is moving from Sasakin building down to Sky Junction and performing the same experiment, in as much as it's moving with uniform motion, the law will be the same. And that is what that is telling us. Regardless of the velocity or the velocity of the source of light or the experiment, it remains the same. That was what Albert Einstein proposed. So here, also including the Maxwell's equation, is the same. Including the Maxwell's equation is the same. So, however, the observation continued. Scientists were actually observing things. So, and later on, after Einstein proposed those two, all observers will see the light flashes go by them with the same speed. All observers, no matter how fast the guy on the rocket is moving, they will see the same thing. So, which means the speed of observers do not matter under the Einstein proposition. The speed of the observers do not matter. No matter how fast the guy in the rocket is moving, he will always see that the lightning, the flashes, is at the same speed as the person observing on the earth. So they'll both see it as what? As C. Now, even when the light flash is traveling in the opposite direction, you can see this is the opposite direction to the person in the rocket. Both guys see the light flash travel past with the same velocity. With the same velocity. Now, another observation. If there's a gun battle, a gunfight, now there are two observers now. She shoots, he also shoots. So both of them, they shoot. And you have an observer here. This is the observer. You will see both shots fired simultaneously. Take note of simultaneously. What he will observe is that both of them are shooting at the same time. He will observe that both of them are shooting at the same time. Why? Because he is what? He's stationary. A stationary observer. He will see both of them shooting at the same time. Now let's now observe if he is moving. What happens? What will be his observation? Viewed by a moving observer, you can see he's moving in this direction. So definitely, he has a speed. Definitely, he has a speed in that direction. So what will be his observation? Viewed by him, he sees the cowboy shoots first and the cowgirl shoots later. Why? Because now he is in motion. He is currently in motion in this direction, towards the direction of the man or the cowboy. So you will see the cowboy shoot first before this. Because he's moving in the direction, he's approaching this boy. So what he sees is quite different from when he was stationary. Another one, what happens here in this situation? So just like it happened the other time, you will see the girl shooting first before the cowboy, because he's approaching the source. But were it to be stationary, you will observe that both of them were shooting at the same time, simultaneously. That they were shooting at the same time. So he sees the cowgirl shoots first and the cowboy shoots later. Now, like I said, take note of simultaneously. Events that occur simultaneously, according to one observer, can occur at different times for other observers. That's the implication.
Yes, sir.
Yes?
This issue of simultaneous, of course, yes, we need a simple explanation of it. I believe that can help us when we are studying. Is it that the motion, the state of the motion of the observer is the same with the meaning of the simultaneous?
The simultaneous will come to play a role when we are really discussing about time. And that's where we get to. Because what Einstein was proposing, Einstein ignored both the speed of the frame of reference, that of the observer, and the time the event took place. It was ignored. And that was the reason why it got to a level where, performing the Michelson-Morley experiment, the Maxwell's equation could not be explained. It couldn't be explained under the Michelson interferometry experiment. So another law now came and said, no, we need to consider the speed of the observers as well as the time the event takes place. One, from the example I have cited above, if you have the cowgirl and you have the cowboy, you have the cowboy shooting. If the observer is stationary, yeah, it will assume that both of them are shooting simultaneously, because the sound that will come to him or the light from the guns that he sees, he will see them at the same time. So that is what is being called simultaneous. But if the observer now start to move towards this, he will see them as not being simultaneous. Now the observer is in motion relative to both sources. So if he's approaching this, he sees this as being the first person to shoot. But if he's approaching this, he sees the cowgirl as the first person to have shot. So that is what is observed. But as we progress now, we'll still see how simultaneity comes to play a role. Because if the time is not considered, there is no way we'll be able to explain special relativity again. And from the physical class, one of the examples I explained was you have like a lungi now. If you discuss about lungi, you have observers at the control tower of the airport. They will announce to you at the airport that the time the plane will land maybe is 4 p.m. However, the pilot in the plane, we have different time completely, because those at the control tower are stationary. While the plane is approaching the airport, the plane is in motion. The only thing that will make them to have an actual timing the pilot is observing, it is only when the plane is moving with uniform motion. But the moment it is not moving with uniform motion, the time the pilot will observe will be different from the time observed at the airport. There might be a difference of maybe 1 to 5 minutes between the time observed. Why? Because the plane is moving from one inertial frame of reference to another frame of reference before it gets to the airport. So because it's moving from one frame of reference to another frame of reference within the sky or the cloud and whatever, the speed varies. So the time will change. And that was what gave birth to what we know as the twin paradox. And also the length contraction. The twin paradox deals with timing. It's as a result of simultaneity. Are the events occurring simultaneously? But it got to a level where the extents proposition of hypothesis couldn't explain certain things. So the relative motion of where events are taking place matters a lot, as well as the time the event is taking place. Brima, have I been able to pass a message?
Yes, it's now clear.
Okay. So as we progress, you will see that. So it now affects all laws of physics. So later on, we will be able to see that the laws of physics are not the same in all frames of references. Now, this is a light clock. So you can see the way the light is moving. You can see the time is changing. That's the mover's frame. The timing changes from one stage to the other. Now, these are events in a coordinate. Can you see? X, Y coordinate. These are two events. X1, event X1 taking place at this coordinate, and event X2 taking place at this coordinate. You will observe that it has its own position and timing, while this also has its own position and timing. And definitely because of the difference in position and timing, it will give birth to different speeds. It will give birth to different speeds. So this is the timing of the event. Except both of them have the same speed, that is when you can talk about the time of the event being the same. But if they have different speeds, it will never be the same. So if they have the same speed, that means when you divide this by this, it gives you the same thing as dividing this by this. Now, prior to Einstein, everyone agreed the distance between events depends on the observer, but not the time. Prior to Einstein's proposition, everyone agreed that the distance between events depends on the observer. And that is the more reason why if you have a football match, just like I said, you have the goalpost, and you have a player, an opponent. If the referee blows, maybe the referee is here, somewhere here. If the referee blows that is offside, then when you come here, prior to Einstein, everyone agreed that the distance between events depends on the observer. What he will see, the referee here, will be different from what a linesman here will see. This is the referee. Another linesman might be somewhere here. What he will see will be different. And that was the reason why FIFA had to introduce the VAR to resolve that problem. Because the distance between events depends upon the observer. So the distance the player moves from here to here before he was offside, as seen by the linesman here, will be different as seen by the referee and as seen by the linesman that is here. So that was before that. So now at the end of the day, so sorry about that. I think there was a Can you see my screen again?
Yes, sir. Yes, sir.
Okay. Okay. So now, just like I said, that was the reason why FIFA had to introduce the VAR, so that to unify what all the officiating men are seeing at the same time. So prior to the proposition of everyone agreed the distance between events depends upon the observer. So the distance between even picking a bottle from here and being broken by a child varies from one observer to the other observer. If both father and mother are sitting down here, what they will see, so the distance between the breaking of the bottle will be different. It depends on the observer, what he views. So that was what was in quotations. Now, Einstein discovered that there's no absolute time It too depends upon the state of motion of the observer. Upon the state of motion of the observer. So Newton started the whole show. He was discussing about space and time. If you remember our physical class, we had this in one frame of reference, XY, you have this, you have this. This frame of reference 1. And we also add another frame, another frame of reference, prime, 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 and prime, which we use to solve problems. That was Isaac Newton. That the law of physics is the same. You know, Einstein came to explain that as well. But it got to a level where Einstein could not explain the Maxwell's equation of electromagnetic radiation. So for Newton, he discussed about space and time as completely different concepts. But Einstein said these are two different aspects of the same thing. Two different aspects of the same thing. So it now depends on the observer. Depends on the observer. How are the times seen by two different observers related? We can figure this out with simple HS level mathematics. Now, we have this. Catch ball on a rocket ship. You have a rocket ship, that means you have a rocket traveling. But these two girls are busy playing inside the rocket. The two kids. So the girl catches the ball, maybe thrown by the boy. So we will now want to see the time he was able to pick it from the time the ball was thrown to the time it was being caught by, or it was being caught by the girl. But the distance between them is 4 meters within the spaceship. Now, the time recorded was 1 second. So how do you calculate the speed? It will be what? Distance divided by what? The time. So you have the speed as this. So that is what you observe. If we move further, that particular event, if we look at somebody on the surface of the earth, location of the two events is different. Location of the two events is different. Now, if you look at here, the clock was in the spaceship. But when you come here, the clock was where? On the surface of the earth. So you have an observer on the surface of the earth. So how is he going to view the speed? So location of the second event is different. So the elapsed time is the same. He sees the time being the same. But what is observed here? You can now see that the speed observed by somebody on the surface of the earth is 5 meters per second compared to the 4 meters per second that was calculated within the spaceship. Because they are now in different inertial frame of references. So what is observed within the spaceship is different from what is observed on the surface of the earth. So because it's on the surface of the earth now, we can now see that we needed to introduce a triangle because it's along this side now. So it now became a triangle, a right angle triangle. From both of them, this is 4 meters. Along this side is 3 meters. So in order to calculate the distance here, that will be 5 meters. So 5 meters divided by 1, that's 5 meters per second. So he's trying to tell us that it now depends on the observer. How is the observer viewing that event? What is the state of that observer? Is it in motion? Is it stationary? So the way they view it now differs. Now,
Sir,
yes,
why is the elapsed time the same?
why the elapsed time is the same? Because from our Newtonian law, the law of physics is the same. It's the same. It's not that the law of physics is changing. It is now the motion of the observer or the observers that will now view it differently. That particular thing is not changing. I think you understand what I'm trying to say.
Yes, sir.
The phenomenon is constant. It's not changing. But it now depends on the properties of that observer that is viewing it. They view it from different things, from different perceptions. And that's why even in a company, you have a problem within a company. There's a board meeting. You want to try to solve the problem. The suggestion of board member 1 will be different from board member 2. Will be different from board member, but they will have different perception. But now we are now saying now that it is the location of the observers that will now determine how they view the event. The event remains the same. It's not changing. But the observer, what is their state of their location, their timing, and whatever, the speed. So that is what now determines. The timing still remains the same, but the distance of this observer from the lady picking the ball is 5 meters as compared to the 4 meter here. So initially the clock was in the spaceship here, but here now on the surface of the earth. So they view it as different, as being different. So the same thing here, light flash reaches the girl, yeah. And that's what we have there. Now, seen from the speed has to be the same, but the distance is longer. Time must be longer. So as seen from the surface of the earth here, what the observer on the surface of the earth, what he views is this. He views this as the speed remains the same. The speed at which the ball moves from the boy to the girl remains the same. But the distance seems longer because along this route is about 5 meters as calculated. So the time must be longer. Time as well must be done longer. The time between the events must be longer. Now we have this. How is the timing we are discussing about related to the time on the moving clock? The clock on the spaceship is the time on the moving clock, which is this, T0. While the clock on the surface of the earth is T. So the relationship between them is this. That's the relationship between them. Why this expression gamma is equal to 1 divided by square root of 1 minus what? V square over C square multiplied by what? That's all. That's our gamma. And you observe that this our gamma is related to the speed of the object. It's related to the speed of the object. Now, what you can now see with the timing now is this. You observe that time on the moving clock, the one in the spaceship, is this. It has additional time. And that was the reason why I informed you earlier that if you have a plane moving towards Lungi, the time of landing or that will be announced by the airport official will be different from the time the pilot sees. One, because the airplane is in motion with a speed v. However, to really know the time of clock on the surface of the earth, it is additional time multiplied by this. So when you look at this equation now, or here, it shows that the time observed on the surface of the earth will be more than the timing that will be observed within the spaceship. Because there is additional time to that of the spaceship, which is gamma, for us to really know the actual timing. Than the actual timing. So here, and that is the reason why if you have twin, if you leave one on the surface of the earth and one travels to space, that is why you find out that one will be older than the other twin based on this equation. And this equation is what we refer to as a time dilation. Is what we refer to as a time dilation. So these are part of the consequences of the postulate. Time dilation is one. So you observe that the timing observed on the surface of the earth is more than what is observed within the spaceship that is moving. Based on this.
Yes, sir. Yes, sir.
In order to get this, you must multiply additional time by the time observed within the moving clock or moving frame.
Yes, sir.
So any question?
Yes, sir. Just want to ask this question.
Okay.
The event is only happening inside of the moving clock or the rocket or whatsoever is moving.
Yeah, spaceship, yeah.
Spaceship. And an observer is on Earth.
Yes.
Looking at the event happening inside the spaceship, right?
Yes.
Okay. So he has his own clock on Earth.
Yes.
And also the events that is happening inside the spaceship, there is also a clock in there.
Yes.
Okay.
And those driving the spaceship also have their own time there.
So they are recording the event at the same time.
Yes, they are recording the event at the same time.
So what they find out that is at the end of the event, the man on or the observer that is on Earth find out that his time is a little bit dilated.
Yes. Yes.
So
the observer on the earth Observe that its own time is dilated by this factor. By this factor that I've written here. This factor that I've written here, we refer to it as the Lorentz factor. This factor, which is this, which is what you have here, is called the Lorentz factor. So it was Lorentz that came to solve the problem of not being able to explain the Maxwell's equation. And that's why we have what is called the Lorentz transformation. We have the Lorentz transformation. We have the Lorentz transformation. So by this factor, this was dilated by this factor, the Lorentz factor. So you are correct. Any other question? Any other question? The answers of question, let me move on. Now, this is we just want to look at the properties of that gamma, which is the Lorentz factor. Now, which is this? So suppose that you have V, the V here is equal to this of C. So if you bring it here, you will have this. You can see this crosses out. At the end of the day, gamma becomes what? This value. So if you continue further, if it's 10% of C, you bring it here, it changes to this. So if you continue to fill in this table with the necessary values, as you adjust that, you have, if you move to 0.5, you can see the Lorentz factor is increasing as the speed increases. Can you see? It continues in that manner until you fill up this table. Can you see now that the Lorentz factor increases as the speed increases, which is our V? So this is what you have. As the speed increases with respect to C, and we all know that our C is the speed of light, you observe that the gamma, the Lorentz factor, increases with that speed. So other values. By the time you are now getting to 1.1 of C, you can see you start having imaginary numbers. Start having imaginary numbers. So this is what you observe here. And this is a sketch of the curve, a plot of this. You can see there is an increase. Can you see the increase? Yeah. As V is increasing. But at this point, your V is equal to C. That's why you have this straight line. So that is what you have. So any questions so far? From all that has been explained.
Yes, sir.
Okay, what's your question?
Yeah, under this Einstein hypothesis, from our knowledge what we've learned under electrodynamics, the second law of Einstein that states that the speed of light in empty space is same for all inertial observers.
Yes.
So now the speed of light in empty space, how about now the speed of light in dielectric? But what we did is that we proved that the speed of light in dielectric is not the same as the speed of light in free space or in medium.
Yeah,
So
under the Maxwell, yeah, you are correct. You are correct. It's not the same. In free space is not the same as when you have it in a dielectric. Yeah.
okay. So that means the law only holds for vacuum, for all vacuums.
Yes, it holds for no, for all vacuum because it's lightweight. So it's the same in all vacuum.
Yeah. So if an event is happening, maybe I don't like maybe inside, or let's say in a dielectric material, are we supposed to consider the postulate of Einstein instead, or we have to negate it?
If it happens, if the event is within a dielectric, for
Yeah.
a dielectric, if it is happening in a dielectric, there's a Maxwell's equation that involves it happening in the dielectric. So definitely you can say it is the same. We cannot ignore, except when it gets to a level where it becomes imaginary or whatever. Because as the speed increases, because if you allow the electromagnetic to pass through a dielectric, electromagnetic radiation, passing through a dielectric, it depends on the speed of the electromagnetic radiation. So the speed with which it's coming with that will pass through the dielectric also will determine something of this nature that I was discussing. It will give us something like this. So as the speed increases, it will enhance the Lorentz. It will enhance the as the speed increases, it will enhance the Lorentz factor.
Yeah.
So that is what you observe. It depends on the speed at which it is being propagated through the dielectric.
Okay.
So it will give us something closer to this table until it becomes. So if it is larger than C, we are coming again with another thing. Those were some of the things I taught in my two last classes, the physical ones, the physical classes. So you can see that once the V is equal to C, what happens to the Lorentz factor? It becomes imaginary. But if the V is larger than C, oh, complete imaginary number. So that was what Lorentz transformation came to explain to us. One of it is that your V must not be greater than C. Your V must not be greater than C. It must not be greater than C. So it tells us that whatever speed we are considering, there's nothing on the earth that can travel more than light. So that is basically what you observe. Any other question? Now, in the absence of question, we have seen that as the speed of the object or the speed of the event we are considering is approaching the speed of light, it tends to be unreasonable and unattainable. So the same thing here. You have this, but your gamma greater than 1. Your gamma is greater than 1, then you have T greater than what? T naught. You have T greater than T naught. So what we'll be discussing is time dilation. We also discuss about the length contraction. So you have an observer in a spaceship in uniform motion, trying to measure the length of a ruler. And you can see it's moving with speed of V. Now, if you observe that the length of the ruler is L naught, what will be the measurement by somebody on the surface of the earth? So this brings us to the length contraction, and the formula for length contraction is this. So if you cancel this V and this V, you are left with this. You are left with L L is equal to L naught gamma. So it then shows that L gamma will be equal to L naught. So it shows that the length is contracted as measured by somebody on the earth. So now, if the length here is contracted, while what is observed here is smaller than this. And that's why we refer to it as the length contraction. So the length measured by somebody on the surface of the earth will be shorter.
No, I I thought that the man in uniform motion will measure the contracted length. As a reverse on the man that is stationary, we measure the proper length.
No, you can see the shorter as an exclamation mark. Is that clear? So the length measured here in the spaceship, this is L. And the one measured on the surface of the earth is L naught. So you observe that the man in the spaceship measures what? A shorter what?
A shorter length.
A shorter length. And that is what is referred to as what? As a length contraction.
Wow.
So I hope you understand this. Time dilation, and that was what led to the twin paradox. And you also have the length contraction as well. So though it's still the same thing, if this is a meter rule you use in the lab for experiment, 1 meter, it's still the same 1 meter. The only thing is that because this is in motion, but the motion is in the V must be less than what? C. That's the condition. It must not be more. So with that, that is what is observed.
So the man in the spaceship is measuring the proper length.
The man
in the spaceship is measuring the proper length.
Yes. So the man in the spaceship is measuring the proper length. Why what is observed in the on the surface of the earth, you can see it will definitely have an additional term going to be this to eventually give you the proper length. It's inversely proportional. So this is what you observe as is trying to get. So the same thing applies to mass. You can see that what happens to the time appears to have happened to the mass. Time, mass. But you have the length the same thing that happens to the mass. You can see that the mass increases by a factor of this. Mass increases by a factor of that. So from what you have here, mass of an object when it is at rest, rest mass, which is this. It is smaller than m, mass of a moving object. That one will increase by this factor. So the rest, do you have questions? Do you have questions? So in summary, moving clocks run slow. Moving objects appear shorter. Moving object mass increases. So those are the summaries of what we have discussed today. Discussed about time, we discussed about length, and we discussed about the mass. So it can. So what we now have is, I think we can stop here for today. So by next week, we will complete the remaining slides, and we'll eventually start solving the problems. I will solve the problem I gave you as the assignment. That is what I'll be doing. I will solve those problems. So I hope it is clear.
Yes, sir.
Okay. So we'll solve all those problems together before your exams. When is the exam commencing?
March, sir. March.
Okay.
But
Maybe throughout March. It's okay. It's okay. It's fine. So that's what I have for you today. So we'll continue on Monday. On Monday. So I think you still use the same link that I sent to you for Monday class. That's the quantum. So for the quantum, we'll just begin to solve those problems together. So there's no need going through revision. So we'll start solving the problems together. By so doing, you will get where and where you missed what you submitted. But my observation is that some of you did not submit. Some of, maybe all of you, I think all of you, I still have the record here. You all submitted the relativity. But the quantum, I think it's just about 3 of you that submitted the quantum. It's okay. We'll solve the problems together on Monday. We'll start with solving them together, all the problems for quantum. Why on Wednesday next week, by Wednesday, we'll finish this up and we'll start solving the problems I gave you together. So I hope it is clear.
Yes, sir.
Okay, Abdullah, what do you
Yes,
have
sir.
to say?
I don't know. Yes, sir. I don't know if you received my assignments on both quantum and relativity.
Both quantum and relativity.
Because I had
What's the
problems
name?
with
Abdullah Basum.
Abdullah Basum.
I
Yes,
only
sir.
received relativity. The record is here. I received 1, 2, 3, 4, 5 of quantum.
I sent
received,
both to my Google Drive. I don't
so
know.
I received
Because
full
my
from
Gmail
Sheikh
was giving
Abangura.
me.
I received the 2 from Sheikh Abangura, from Nofisa to Sese, Maria Makonte, Adin, Mary, and Awanotu Kamara. So those were the ones I received full for both modules.
I actually sent mine to my Google Drive because
Okay, through your Google Drive. I will try to look for it. I will look for it.
Okay, sir. Okay.
I will look for it. So,
The attachment was okay.
so
My
I'll
Gmail,
see
so
you
I
on.
decided to send it to my Google.
I'll see you on Monday, same time, which is 2 for Sierra Leone and 3 here in Nigeria, 3 p.m. here in Nigeria. So you still use the same link.
Okay.
I think I set it as recording. So still the same link for both classes. So it doesn't change. It doesn't change. So see you on Monday. So thank you. Do have a wonderful weekend.
Okay, sir. Thank you too.
Okay. So I'll share the recordings with you once it's ready. I'll do that.
Okay, sir.
Okay. Okay.